Okay, thank you everyone, and thank you for the introducing. Welcome to my talk. And today my talk is about our latest work, which is named Support Triangle Machine. Actually, when people first hear about this title or saw this title, they just thought of what the hell is that? Is there any relationship with the support vector machine? But from my point of view, there's no connection with the SVM. And support triangle machine is just an approximation lifting technique that can be used in the formal verification. I will show you now. So in this talk, I will first cover the background and then present our goals and our works. And after that, I will present the problem formulation. And the next is our main part, support triangle machine details. And before closing this talk, I will show some evaluation results that can help you to gain some confidence in our technique. So first, the background, the formal verification of deep neural networks. So I think as you know that in the last decades, the deep neural networks has been increasingly popular due to their exceptional performance in many challenging tasks. But researchers also found that deep neural networks can subject to security concerns. This is a typical example from a well-known paper, and as a result, before deploying deep neural networks into real scenarios, they must be formally verified. There are roughly two kinds of methods: exact method and approximate method. Exact methods are really precise. They are based on SMT solving or linear programming or etc. And the problem with the exact method is they are inefficient and they cannot scalable to non-toy neural networks. And for the approximate method, they are based on the approximation or the methodology called abstract interpretation. And one of the main challenges in the approximate method is how can the nonlinear activation functions are handled. So based on the way they handle the nonlinear functions, they can be classified into single-neuron approximation method and a multi-neuron approximation method. And in single-neuron approximation method, they just ignore the relationship between different neurons. So they only consider one input neuron for at one time for the activation function. As a result, the input-output pair just stays in the 2D space, and only the planar geometry needs to be considered. As a result, these methods are usually simple, straightforward, but the result is less precise. And in comparison, multi-neuron approximate method, they try to consider the relationship between different input neurons. And indeed, they consider a group of input neurons, and thus the input-output pair are in the 2ND space, and where the high-dimensional geometry must be considered. As the result of multi-neuron approximation method are more precise, but their design and development are very complicated and error-prone. So the red figure just shows some examples. So our goal is try to make the multi-neuron approximation construction much simpler and much easier. So up to now, we have published two papers. The first one in Popo 24. It is called ReLU approximation. And it tries to approximate the convex over ReLU functions by assembling selective faces of the convex hull in the high-dimensional space. And the other one is the paper I present here. It's called support triangle machine. It tries to bridge the gap between the single-neuron approximation method and the multi-neuron approximation method. And the idea is just to do the approximation lifting. I'll show you how it works. And before that, I will formulate the problem. So here's a simple problem formulation. We call it Convex Approximation Lifting. It takes a triple as the input, where the S here donate to the single neuron approximation, and it try to derive the M, the multi-neuron approximation, and the other two inputs are the X, which donate to the input convex set, and F is the exact transformation. So for example, in the neural networks, F can be the ReLU function, the sigmoid function, or the hypertangent. Yeah, that's it. And we use a technique, we call it HP pairing technique. It's short for the hyperplane point pairing. It says that an n plus 1 dimensional hyperplane can be determined by an n dimensional hyperplane and a point of it. It is very abstract. So for example, when n equal to 0, that means a line can be determined by 2 points, 2 distinct points. And when n equal to 1, that means a plane can be determined by a line and a point out of that line. And in the high dimensional space, the property also holds. And in proposal 24, we have applied the technique to do the ReLU Hall approximation. The idea is very simple. We just need to track how its vertices and hyperplanes are transformed using the ReLU function. And after that, so for example, here the vertices A, after the ReLU transformation, it becomes A prime, and this edge DE, after the ReLU transformation, it becomes D prime E prime. And after that, we can assemble one hyperplane here. Just take A prime, D prime, E prime. That is, so the idea is simple, but the implementation can be a little more complex. Yeah. And after that, we found that the HP pairing technique might be more powerful than that. It can go beyond the ReLU Hall approximation. And actually, we have two observations. The first one is we can use that technique to construct multi-neuron approximation for any contiguous and a two piecewise linear function. This is very straightforward. And how about other type of functions? We can also do that. I will show you later. And the other observation is that we can even use the technique to construct the single neuron approximation. This is seems trivial, but this is a very important observation. Because it indicates that the technique might provide us a unified way to construct the approximation construction for both multi-neuron setting and the single neuron setting. And it also suggests that there might be some relationship between the single neuron approximation and the multi-neuron approximation. And it's to inspire us to explore further, and it also makes our STM is possible. So in essence, the HP pairing technique that can link the single neuron approximation and the multi-neuron approximation through a structure, through the triangle structure. That is the key. And for the triangle, the two sides here, just provides the transformation for the hyperplanes and the vertices. And the other side just donates the boundary of the approximation. And it shows us how we should pair the hyperplane and the vertices. And one naive question, what if we do not have the triangle? We can create one. For example, here suppose this is the F and this is the over approximation. We can create a triangle here. Then we can apply the same technique. So here is a formal definition of this support triangle. And we call it a support triangle because it is a triangle and it support the boundary of the approximation. And we have distilled the triangle lifting technique just from the Popo 24, how the Ralujo approximation is made. And that's it. And another property that is really, really interesting is the compositionality, which is very beautiful in the computer science, I think. And we found that for the single neuron approximation, we can decompose them very easily based on the following rules. So for the single neuron approximation, we can first split it into two parts, the upper part and the lower part. For example, here, suppose this is the function f, and this is a single neuron approximation. So we first split it into two parts, the upper part and the lower part. And for each part, we can decompose them into several linear parts. For example, for the upper approximation, we can split it into two parts, the first part, the second part. And each linear part can be lifted independently. And the next is, after lifting, we can compose the final approximation by just conjoin them together. This is a very important property, and proving them can take time. It's in a paper. If you are interested, you can look. You can refer to our paper. Yeah. So with all above, here's the overall algorithm for the STM. It is an iterative algorithm. It processes each output coordinate incrementally. And for each output coordinate, it decomposes the single neural approximation into linear parts and lift each linear part independently and conjoin the lifted approximation together. Yeah, and then with this approximation, it can go to the next round to process next output coordinate. And there's also one issue we haven't visited yet. What if there are multiple support triangles? And actually, there are usually an infinite number of support triangles. Which triangle should we select? Optimally, we would like to have the one that leading to the largest precision gain, but the search space is pretty huge. It needs to consider the X and F, and also the S. So we propose a heuristic here. We just choose the triangle with the largest area. That's it. So here's our evaluation. We have evaluated 5 typical functions: liquid ReLU, sigmoid, hypertangent, exponential, square. And we checked 2 types of single neuron approximation, boxes and polyhedron. And we evaluated based on the precision, efficiency, and output complexity. And we try to evaluate the effective of our heuristics, and we try to check the performance on CL problem and DNN verification tasks. As I'm not a guy who are good at the experimental experiments, I just show you some results, and I won't go to very details. So for the triangle selection heuristics, the result just so that our heuristics usually cannot find the optimal solution, but the precision loss is still very small. And on the CL problem, CM is sort for the convex approximation lifting, and we have so many settings, and the result so that our method is more precise than the Cartesian product, but less precise than the convex whole computation, but it's more efficient. And for the sigmoid and the hypertangent, we also compare with the state-of-art method, the Prima. The result is there. And the last one is on the verification task, we have trained several neural networks with liquid real rule activation functions, with sigmoid and hypertangent activation functions. And the conclusion is that our method is more precise than the single neuron approximation method, and it can achieve the same level of precision with the state-of-art multi-neuron approximation method, and it is more efficient than that. That's it. Yeah. So in this work, we try to bridge the gap between single neuron approximation method and the multi-neuron approximation method through lifting, and we formulated it as a novel problem, convex approximation lifting, and we invent the support triangle structure and derive a triangle lifting technique, and we introduce the STM to solve the L problem, and we do some preliminary evaluations. That's it. Any questions?
Yep. All right. Are there questions for Jiaying? I will start with a question. If we have techniques like this, what does this tell us about the design of the activation functions themselves? Right? Does it make sense to design activation functions that are better approximated in this multi-neuron setting?
So your question is about does this approach can tell us some lesson on designing activation function?
That's right.
This is a really good question, I think. But I think in the community, usually we cannot control the design of the activation function, right? Usually the AI guys can come up with some ideas, and we need to handle these functions. But from my point of view, if we can have some control, we would like to have the function as simple as possible, I think. Yeah.
That's a funny but realistic answer. Yes. Other questions about this technique?
Yeah, thanks a lot for the great talk. I have a question about that. Yeah, I'm Jiaying from Chunxue University. So I have a question that, so at the beginning you said that the existing approaches about using the multi-neuron approximation is hard and is difficult. So it's complicated. I wonder, what do you mean concretely, like the computational complexity or the efforts that are taken by the developers?
Okay. So the question is about what I've said is that multi-neuron approximations are complicated error-prone. What does the complicated means? It is it can be referred to the complexity, but what I said is the design and the development of this method is really complicated, really difficult. Yeah.
I have another question for you.
Yeah.
Have you considered using these approximation techniques, outside deep neural network verification? I could imagine potentially using this in like collision detection and graphics or something like that. Do you have other applications in mind?
So the question is about are there any possibilities we can apply the same technique to other domains? For the domains you mentioned, frankly speaking, we haven't considered that yet, but we have considered some other things in the software verification. I think both the HP pairing technique and also the decomposition is very general. I think it should be promising to apply the same technique or just modify some part to to be used in the software verification. That is my thought.
Okay, very cool. Please give Jiaying a round of applause again.